Okay, so here in example 1, we want to try to apply what we've learned so far. And so without a calculator, let's see if we can match the polynomial function a, b, c, or d with its graph and then try to explain our choice. And so if we look at a has a leading term of negative 7x cubed. And so a has a negative lead coefficient and an odd degree. And so from our leading term test, from that table on the first page of your notes, what does that mean about the end behavior? Well, it means that it's going to be up and then down. And again, that's very informal. You could also say infinity, negative infinity. That's maybe just as informal. I'm not looking for formality here. I'm just looking for, can we understand the concept? And we'll get more formal as we go along. And so if we look here, which of these four functions have the up-down behavior? And that would be these two in the right-hand column. So this choice here and this choice here are the ones that have up on the left and down on the right behavior. And so what's the difference in these two graphs on the right? Well, if you look at the one on the top, how many turning points do you see in the graph? Well, I see one down here that's actually a minimum. I see what I would call a horizontal tangent right here, which counts as a turning point. And then I also see a turning point right here. So that is a total in this graph of 3 turning points. Now, remember from our theorem, that very last definition that we had in Roman numeral 1, if a function has 3 turning points, that means it has to be at least a degree 4 polynomial, because a degree n has at most n minus 1 turning points. And so if you've got 3 turning points, that means it's got to at least be degree 4. And this polynomial in letter A is not degree 4. It is only degree 3. And so that means it cannot be that top graph. It's got to be this bottom graph, because the bottom graph has only 2 turning points. And so since it only has 2 turning points, that means it has to be at most, or at least, I should say, at least degree 3, and that's what letter A is. And so this graph corresponds to letter A. Now, can we find another function from our choices that has the same end behavior, but is at least a degree 4 like it needs to be? So take a look at your other choices, and let's see what's going on. Well, in letter B, this is a positive and odd, and so that's not going to have the same end behavior as letter A. What about letter C? That's a negative and odd, and so it is going to have the same end behavior as letter A. And letter D is positive and odd, and so the only other one that has the same end behavior would be letter C, and letter C is degree 5, and so therefore it can have 3 turning points. It could have 4 turning points, but it doesn't necessarily have to have 4. It just can have at most 4, and apparently it has 3. And so this is going to be my choice for function C. Now that obviously leaves B and D for the other 2 graphs, and so let's take a look here at B. B has a positive lead coefficient and odd, and so positive and odd leading term means that the function is going to have the end behavior down and then up, or even less informally, or less formally, I guess I should say, negative infinity on the left and positive infinity on the right. And so as you can see, that would correspond to both of these graphs. And so how do you determine which one is B and which one is D? Well, you have to look at the number of turning points. And so for this particular graph right here, there are 2 turning points, which means that it has to be at least a degree 3 in order to have 2 turning points. And this particular graph has 1 turning point here, 1 turning point here, and 1 turning point here. And so this bottom graph has 3 turning points, which means that it has to be at least a degree 4, and that means it cannot be letter B as in boy, it has to be D as in dog, and that means that this one is letter B, which would make sense because letter B was positive and odd. It's a degree 3, which means it can have at most 2 turning points, and so that's how we're determining that based on the theorem at the bottom of Roman numeral 1 and our leading term test, which we learned in that table with the 4 pictures. Okay, we are skipping example 2. We're going to move to example 3, and I'm just going to have you describe the end behavior using limits here. And so the end behavior of a polynomial function is all determined by that leading term. So notice that this polynomial in letter A is already written in standard form. So the leading term is x cubed, which has a positive coefficient on it and an odd exponent. And so think about, what does positive and odd mean? It means it's going to be down and then up, just like y equals x would be. And so that leading term determines the end behavior. And so we're going to write this more formally now with limit statements and say that the limit as x approaches negative infinity of f of x. Well, if you take a look at our picture, that would be this end of the graph, and we drew that going down to negative infinity. And then the limit as x goes to positive infinity of f of x, that's going to be the right end behavior of the graph, and you can see that we drew that going up to positive infinity. Now in letter B, looking at the lead term, that is 2x to the 4th, and so that's going to be positive and even this time. And so if I think about what that means I'm going to have a graph that goes up in both directions, and so therefore both of my end behavior limits are going to be positive infinity. The limit as x goes to negative infinity of f of x, that's the left end behavior, that will be positive infinity, and the limit as x goes to infinity of f of x, my right end behavior will also be positive infinity. So one more time, that leading term is what determines your end behavior. All right, one more time in example 4, so hopefully you're getting the hang of this. In letter A, we've got a leading term that has a positive lead coefficient and an even exponent, and so just like letter B of example 3, this is going to be up and up on our ends, and so therefore both of my end behavior limits are going to equal to positive infinity. And make sure that you're getting good at writing these limit statements. For some reason, that's one thing that students maybe tend to struggle with just a little bit, and so if you're having trouble understanding how exactly these need to be written, please let me know and I'll be happy to help. Letter B, the leading term has a negative lead coefficient and it is odd. And so what that's going to look like is it's going to look like up to the left, but down to the right. And so therefore my two end behavior limits are going to be the following. Limit as x goes to negative infinity of f of x. Well, that would be the left end of the graph, and so that's going to be positive infinity. And the limit as x goes to positive infinity of the function f of x is going to equal to negative infinity, since that's my right end of the function, and you can see that the y values are decreasing without bound.